This lecture is about what's probably the most important way to construct a carbon skeleton, and that is the Diels-Alder reaction. We're going to learn how to use the Diels-Alder reaction in natural product synthesis.
In a Diels-Alder reaction, a conjugated diene, that is, pi sigma pi, and a dienophile, which is an alkene or alkyne, combine to form a cyclohexene from the alkene, or 1,4-cyclohexadiene from the alkyne. Note that the process occurs in a concerted manner, that is, all the electrons appear to flow simultaneously from one pi bond to the next. In addition, three new bonds are formed: two sigma bonds between carbons 1 and 5, 4 and 6, and a new pi bond between carbons 2 and 3. Since there are no obvious nucleophiles or electrophiles in Diels-Alder reaction, we need a new theory called frontier molecular orbital theory, or FMO, to explain it. Electrons act like waves. Now imagine an electron wave with a positive crest and a negative trough. If the crests or the troughs combine, there's an additive effect. Make the 2D electron wave a 3D atomic orbital, and these crests and troughs become orbital phases. The phases can be given positive or negative signs or opposite shading. Same phases combining head-to-head make a stable, low-energy molecular orbital or sigma bond. Now, if the positive crest combines with a negative trough, that cancels out the waves. In 3D, the head-to-head interactions of the atomic orbitals don't overlap, they repel, creating an unstable, high-energy, antibonding molecular orbital, sigma star. There is a region of zero electron density called a node between the atoms. For side-to-side overlap of p orbitals, you get a low-energy, stable molecular orbital, a pi bond, when the overlapping orbital phases are the same. If the interacting orbital phases are opposite, there's repulsion, and you get an unstable, high-energy, antibonding pi molecular orbital, pi star. Again, there is a node between the interacting orbitals, a region of zero electron density. Based on certain symmetry rules, FMO theory allows us to construct pi-like molecular orbitals for the diene and dienophile. The diene's 4 p orbitals overlap to form 4 distinct molecular orbitals. The lowest energy or ground state molecular orbital is all bonding and has no nodes, since all the overlapping p orbital phases are the same. From the 4 pi electrons available, 2 electrons are placed in the ground state molecular orbital. The next higher energy molecular orbital also has 2 pi electrons and is called the highest occupied molecular orbital, or HOMO. This molecular orbital is net bonding with 2 pi interactions and 1 antibonding pi interaction, creating one node. Just above the HOMO, with no electrons, is the lowest unoccupied molecular orbital, or LUMO, with 2 nodes. The LUMO is net antibonding. The highest energy molecular orbital has 3 nodes. Only the HOMO and LUMO are the frontier molecular orbitals that we will use to explain the Diels-Alder reaction. The HOMO of the diene is nucleophilic and reacts with the LUMO of the dienophile, which is electrophilic, in a normal electron-rich diene, electron-poor dienophile Diels-Alder reaction. For inverse electron demand Diels-Alder, the LUMO of the diene reacts with the HOMO of the dienophile. In this situation, the diene is electron poor and the HOMO is electron rich. Now in the Diels-Alder reaction, the diene must have an available S-cis conformation. Note that in the S-cis conformation, the double bonds are both pointing in the same direction. Looks like a C. But if you have two bulky groups attached to the termini of the diene, they will collide, forcing the groups to rotate away from each other and return to the S-trans conformation, which is no good for the Diels-Alder reaction. Cyclic S-cis dienes react faster than the corresponding acyclic S-cis diene because the conformation that is desirable is locked. Dienes react fastest with electron donating groups like oxygen or nitrogen attached directly to C double bond C. Dienophiles react fastest with electron withdrawing groups like C double bond O, NO2, C triple bond N directly attached to C double bond C. Now if you put an electron withdrawing group on the diene and an electron donating group on the dienophile, you get what is known as an inverse electron demand Diels-Alder or IEDDA. This works just fine. In the Diels-Alder reaction, the major kinetic product is endo. In the reaction shown, the Cn points under the larger ring, away from the bridge. That's endo, the major product. When the Cn is pointing toward the smaller bridge, that's exo. According to FMO theory, the HOMO of the diene interacts with the LUMO of the dienophile. The orbital phases combine to form the sigma bonds, but there's also a secondary orbital overlap between C triple bond N and the back lobes of the HOMO, which lowers the activation energy and makes the reaction faster. You can also call these sticky orbitals. Here we have practice problem 1. Predict the major product of each of the following reactions. If no reaction occurs, explain. Note, for the Diels-Alder reaction, the major product is always assumed to be the major kinetic product unless stated otherwise. So here are some considerations. Make sure that your diene can be S-cis. Also, if you're going to form a bicyclic structure, make sure that that's the endo product. Okay, if you have a terminal R group on your diene relative to an R group on the dienophile pointing down or away from you, this is what you do. When the R diene is pointing inward, cis in the double bond, it'll be up or trans to the R dienophile in the product. If the R diene is pointing outward, trans in the double bond, then it'll be down or cis to the R dienophile in the product. The opposite is true when the R dienophile is pointing up. So in the first case, the R diene group is pointing in, therefore it will be up or trans to the R dienophile. In the second case, the R diene group is pointing outward, so when it reacts, it will be pointing down or cis to the R dienophile group. And here are a couple of mnemonics to help you remember this. Up in your business and down and out when R dienophile is down. Down in the valley and get up out of the way when R dienophile is up. Practice problem 2. Predict the major product of each of the following reactions. If no reaction occurs, explain. Note, for the Diels-Alder reaction, the major product is always assumed to be the major kinetic product, unless stated otherwise. Now some considerations for this problem. First, of course, make sure that your diene can have an S-cis conformation, or you won't have any Diels-Alder reaction at all. Secondly, for one enantiomer, always point an R group on the dienophile down, and that way we can apply some of the ideas we just learned. When the dienophile's R group is pointing down, and there's an R group at the terminus of the diene, that R group is pointing out, right? That's its trans on the diene. Then it's going to also be down and out, okay? Down just like the R group on the dienophile. If the R group on the diene is pointing in, okay, it's cis in the diene, then it's going to be pointing up, okay, up in your business. So it's going to be trans to the downward pointing R group in the dienophile. Okay, now let's look at the regioselectivity of the Diels-Alder reaction. You want to match the partial negative charge on the diene with a partial positive charge on the dienophile. This is the same as matching the largest homodiene component with the largest lumodienophile component. So you can see when the R group is terminal, the partial negative charge is at the end of the diene, reacting with the partial positive charge on the dienophile, forming mostly what's called the orthoadduct, where R and Z are next to each other. And if you flip the dienophile, you get the minor meta-adduct. When the R group is in position 2, then the partial negative charge and the largest homo component is at position 1. And when it reacts with the dienophile, the major product is the so-called para-adduct, where R and Z are across from each other. If you flip the dienophile, then you get the minor product known as the meta-adduct. Let's look at some examples of regioselectivity in the Diels-Alder reaction. If R is at position 1 of the diene, then the major product, as we discussed, would be the orthoadduct, where R and Z are next to each other. And again, if you flip the dienophile, the minor product will be the meta-adduct. Data confirms this, and we see that as long as the R group is an electron releasing group, such as O or N, then you're going to get 100% of the orthoadduct. However, if it's a weakly electron releasing group, such as a methyl group, then the regioselectivity is diminished. When the R group is moved to the second position, then as we would expect, the major product will be the para-adduct, and the minor product will be the meta-adduct. Again, the methyl group diminishes the regioselectivity of this reaction. However, it can be enhanced if the Z group is changed from an ester to an aldehyde, some increased electron withdrawing group, so that you get 100% para-adduct formation. Also, the benzene ring, the phenyl group, diminishes the regioselectivity of the reaction, the same as the methyl group. One would expect that other alkyl groups would also have diminished regioselectivity, just like methyl. Practice problem 3. Predict the major product of each of the following reactions. If no reaction occurs, explain. Note, For the Diels-Alder reaction, the major product is always assumed to be the major kinetic product, unless stated otherwise. Now be careful here because you're going to have a mixture of both regioselectivity in your reactions as well as the use of the endo rule. So be very careful when you're examining how all of these dienes and dienophiles come together to form the Diels-Alder product. The Diels-Alder reaction can be reversed. This is known as a Retro-Diels-Alder reaction. Since the Diels-Alder reaction is exothermic, at high enough temperature you can reverse the process, such as with dicyclopentadiene becoming cyclopentadiene. The reaction can also be useful for making aromatic rings. In the bottom Diels-Alder reaction, alkyne reacts with the diene to form an intermediate, and then in a Retro-Diels-Alder reaction, the formation of an aromatic ring and CO2 make the entire process irreversible. In the intramolecular Diels-Alder reaction, a diene is tethered to a dienophile, and at elevated temperature, the Diels-Alder reaction can occur, assuming that you can overcome steric encumbrance. In the example shown, this Diels-Alder adduct is a key intermediate in the synthesis of the natural product 9-isocyanopupoquinone. The intramolecular Diels-Alder reaction is tricky to see, so let's see what we can do to make it easier to understand. We want to rotate the diene around so that the key components, carbons 1 and 4, face carbons 5 and 6 in the dienophile, so that at elevated temperatures you have a successful Diels-Alder reaction. Now, it should be pointed out that there's a lot of steric strain in this transition state, so what really matters the most is lowering that steric strain, not the endo rule, okay, to determine the major kinetic product. Practice problem 4. Predict the major product of the following reaction and draw the transition state leading to the product. You definitely want to build a molecular model of this compound so that you can wrap the diene around to face the dienophile, and that way you'll be able to figure out what the product should look like. One of the most widely used methods for the enantioselective Diels-Alder reaction employs Corey's protonated or Lewis acid activated oxazaborolidine catalyst. If an alpha-beta unsaturated ketone or ester reacts with a diene, only the top face is available, producing almost exclusively a single enantiomer of the endo adduct. In the case of an alpha-beta unsaturated aldehyde, when the diene reacts again at the top face, the major product will be the exo adduct as a single enantiomer. And in the final case, if a quinone is bound to the catalyst, again only the top face is available, and the diene reacts at the least sterically hindered dienophile, or carbon-carbon double bond, to produce mostly one enantiomer of the endo adduct. Here are some rules for predicting the reactivity of quinones toward Corey's oxazaborolidine catalyst. First, the quinone has to bind to the catalyst, and thus the catalyst must pick one of the carbonyls and alpha hydrogens to bind to. The carbonyl that's chosen is the one that's conjugated to the best electron donor. The diene then reacts with the dienophile that's least sterically hindered, and an X group on that diene will stay as far away from the catalyst as possible. Our product is endo and mostly one enantiomer. In the example shown, the triisopropyl siloxy group is our X group, which again stays as far away as it can from the carbonyl that the catalyst is bound to. And that carbonyl is the one that is in conjugation with the methoxy group. Practice problem 5. Predict the major product of each of the following reactions using Corey's protonated or Lewis acid activated oxazaborolidine catalyst. Now remember to use the model for how the catalyst binds to each of the dienophiles in order for you to predict what the product will be. Also, don't forget, only the top face of the dienophile will react. Answers to practice problem 5. In part A, the alpha-beta unsaturated ester binds to the catalyst, and the diene only reacts at the top face to produce the endo product. In part B, the alpha-beta unsaturated aldehyde also binds to the catalyst, but this time the exo product is generated. And in part C, quinone binds to the catalyst. The carbonyl that's bound is conjugated to the methoxy group. The triisopropyl siloxy group stays as far away as it can from the bulky catalyst, and we produce the endo product. In the hetero-Diels-Alder reaction, a diene reacts with a dienophile that's not C double bond C, but C double bond O or N or something like that. But this has to lack a carbon-carbon double or triple bond. For example, an imine can react with a diene, or an aldehyde can react with a diene. The electron-poor heterodiene can also react with an electron-rich dienophile. In this case, the HOMO of the dienophile and the LUMO of the diene are what are reacting. This is the same as inverse electron demand. So as you can see in the example, an alpha-beta unsaturated imine is reacting with an electron-rich dienophile to produce a product. If you're comparing a hetero-Diels-Alder reaction with a Diels-Alder reaction, the Diels-Alder reaction always wins. It's always faster. As in the case of the alpha-beta unsaturated aldehyde reacting with cyclopentadiene. It's the Diels-Alder reaction product that you're going to detect. Hetero-Diels-Alder reactions can also be intramolecular, as in the case of an alpha-beta unsaturated imine reacting with an alkyne to form an intermediate adduct, which, under thermolysis, eliminates alcohol to form a pyridine ring. Powerful enantioselective versions of the hetero-Diels-Alder reaction have also been developed. In one case, Cordova's group has combined 3 components, an alpha-beta unsaturated ketone, formaldehyde, and an aniline, in the presence of a proline-derived catalyst to form a single enantiomer. What occurs is that the proline analog first combines with the alpha-beta unsaturated ketone to form an enamine structure. Then you also get the combination of the formaldehyde and aniline compounds to form an imine. When this imine attempts to react with the diene, it is hydrogen bonded through the NH group of the catalyst, forcing the imine to react at the top face of the diene, giving you enantioselectivity. The regeneration of the catalyst occurs when the enamine intermediate is hydrolyzed, which forms the final product and regenerates the catalyst. Practice problem 6. Predict the major product of each of the following reactions. Now these are all hetero-Diels-Alder reactions, either intermolecular or intramolecular. One important thing to consider is that if you have an aldehyde and an amine, then they're going to form an imine before reaction with a diene. That is, aldehydes do not react as fast with dienes as the imine, particularly the iminium ions, do. So you're always going to generate the imine before reaction with a diene. Of course, if there is no ability for the aldehyde to convert to an imine, then you react the aldehyde directly with the diene. Answers to practice problem 6. In part A, we have an intramolecular Diels-Alder reaction between an aldehyde and a diene. In part B, we have 3 components. The formation of the imine occurs first between formaldehyde and the amine, which then reacts with the diene. Part C, we have an enantioselective hetero-Diels-Alder reaction. You generate an enamine from the catalyst and the alpha-beta unsaturated ketone, and then the imine made from the aniline and formaldehyde is coordinatively placed over the diene to form the single enantiomer upon hydrolysis, releasing the catalyst and the product. Natural product synthesis exercise 1. Retrosynthetically propose a synthetic route to cacinene dihydrochloride via the Diels-Alder reaction using homochiral cryptone as a starting material. Remember to always work backward to structures that contain either a cyclohexene or a 1,4-cyclohexadiene. Answer to natural product synthesis exercise 1. The 2 tertiary chlorides and cacinene dihydrochloride could have been derived from 2 tertiary alcohols by functional group interconversion. The 2 methyls in the tertiary alcohols could have come from 2 equivalents of methyl magnesium bromide reacting with 2 ketones. Now, which ring was once the cyclohexene? I picked ring A because I need the C double bond O in ring B to be able to epimerize the alpha proton from cis to trans. This requires acid or base. The cyclohexene can now be disconnected to a diene and a dienophile. Here you are. See how the positions of the dienes, partial negative charge, and the dienophiles, partial positive charge, match up perfectly for the desired regioselectivity. Here is the actual published synthesis. Natural product synthesis exercise 2. Retrosynthetically propose a synthetic route to acantene via an enantioselective Diels-Alder reaction. Note you already have the cyclohexene in the structure, but you have to work backward to a dienophile, so the dienophile needs an electron withdrawing group. Answer to natural product synthesis exercise 2. First, we have to disconnect the terminal alkene to an aldehyde. We do this to have an electron withdrawing group on our dienophile. Wittig hologenation achieves the aldehyde to alkene conversion. Now, the aldehyde was once protected as an acetal because we need to revert the leftover transalkene backwards to an alkyne via antihydrogenation, and then to an alkyl halide via SN2. Next, we reveal the aldehyde again, which we protected as an acetal. You might think that this is a great time to disconnect to a diene and a dienophile, but Corey's protonated or Lewis acid activated oxazaborolidine catalyst would cause the wrong enantiomer to form, so we need to work backwards to an ester which binds to the catalyst in the correct orientation. Finally, the enantioselective Diels-Alder reaction of the alpha-beta unsaturated ester and diene will furnish the desired adduct. Note that in practice, 2,2,2 trifluoroethyl esters are used because simple monoesters are not reactive enough.